In computer science, a union is a value that may have any of several representations or formats. Or it is a data structure that consists of a variable that may hold such a value. Some programming languages support special data types, called union types, to describe such values and variables. In other words, a union type definition will specify which of a number of permitted primitive types may be stored in its instances, for example, float or long integer. Contrast with a record, which could be defined to contain a float and an integer. In a union, there is only one value at any given time. A union can be pictured as a chunk of memory that is used to store variables of different data types. Once a new value is assigned to a field, the existing data is overwritten with the new data. The memory area storing the value has no intrinsic type, but the value can be treated as one of several abstract data types, having the type of the value that was last written to the memory area. In type theory, a union has a sum type. This corresponds to disjoint union in mathematics. Depending on the language and type, a union value may be used in some operations, such as assignment and comparison for equality, without knowing its specific type. Other operations may require that knowledge either by some external information, or by the use of a tagged union. Untagged unions, because of the limitations of their use, untagged unions are generally only provided in untyped languages or in a type-and-safe way. They have the advantage over simple tagged unions of not requiring space to store a data type tag. The name union stems from the type's formal definition. If a type is considered as the set of all values that that type can take on, a union type is simply the mathematical union of its constituting types, since it can take on any value any of its fields can. Also, because a mathematical union discards duplicates, if more than one field of the union can take on a single common value, it is impossible to tell from the value alone which field was last written. However, one useful programming function of unions is to map smaller data elements to larger ones for easier manipulation. A data structure consisting, for example, of 4 bytes and a 32-bit integer, can form a union with an unsigned 64-bit integer, and thus be more readily accessed for purposes of comparison etc. Unions in various programming languages. C++, in C and C++, untagged unions are expressed nearly exactly like structures, except that each data member begins at the same location in memory. The data members, as in structures, need not be primitive values, and in fact may be structures or even other unions. However, C++ does not allow for a data member to be any type that has a full-fledged constructor destructor and/or copy constructor, or a non-trivial copy assignment operator. For example, it is impossible to have the standard C++ string as a member of a union. Like a structure, all of the members of a union are by default public. The keywords private, public, and protected may be used inside a structure or a union in exactly the same way they are used inside a class for defining private, public, and protected member access. The primary use of a union is allowing access to a common location by different data types, for example hardware input-output access, perhaps bitfield and word sharing. Unions also provide crude polymorphism. However, there is no checking of types, so it is up to the programmer to be sure that the proper fields are accessed in different contexts. The relevant field of a union variable is typically determined by the state of other variables, possibly in an enclosing struct. One common C programming idiom uses unions to perform what C++ calls a reinterpret cast, by assigning to one field of a union and reading from another, as is done in code which depends on the raw representation of the values. A practical example is the method of computing square roots using the IEEE representation. This is not, however, a safe use of unions in general. Structure and union specifiers have the same form. The size of a union is sufficient to contain the largest of its members. The value of at most one of the members can be stored in a union object at any time. A pointer to a union object, suitably converted, points to each of its members, and vice versa. Anonymous unions can also be anonymous. That is, they do not have a name, their data members are accessed directly. In addition to this, they have certain other restrictions like, they must also be declared as static if declared in file scope. If declared in local scope, they must be static or automatic. They can have only public members. Private and protected members in anonymous unions generate errors. They cannot have function members. Simply omitting the class name portion of the syntax does not make a union an anonymous union. For a union to qualify as an anonymous union, the declaration must not declare an object. Example: anonymous unions are supported by C11 and as a non-standard GCC extension. COBOL in COBOL, union data items are defined in two ways. The first uses the renames keyword, which effectively maps a second alphanumeric data item on top of the same memory location as a preceding data item. In the example code below, data item person or EC is defined as a group containing another group and a numeric data item. Person data is defined as an alphanumeric data item that renames person or EC, treating the data bytes continued within it as character data. The second way to define a union type is by using the redefines keyword. In the example code below, data item versnum is defined as a 2-byte binary integer containing a version number. A second data item vers bytes is defined as a 2-character alphanumeric variable. Since the second item is redefined over the first item, the two items share the same address in memory, and therefore share the same underlying data bytes. The first item interprets the two data bytes as a binary value, while the second item interprets the bytes as character values. Syntax and example: in C and C++, the syntax is: a structure can also be a member of a union, as the following example shows. This example defines a variable uvar as a union, which contains two members, a structure named svar, and an integer variable named d. Unions may occur within structures and arrays, and vice versa. The number ival is referred to as symptob, I, uival, and the first character of string sval by either of symptob, I, usval or symptob, I, usval, 0. Difference between union and structure: a union is a class all of whose data members are mapped to the same address within its object. The size of an object of a union is, therefore, the size of its largest data member. In a structure, all of its data members are stored in contiguous memory locations. The size of an object of a struct is, therefore, the size of the sum of all its data members. This gain in space efficiency, while valuable in certain circumstances, comes at a great cost of safety. The program logic must ensure that it only reads the field most recently written along all possible execution paths. The exception is when unions are used for type conversion. In this case, a certain field is written and the subsequently read field is deliberately different. An example illustrating this point is: structures are used where an object is composed of other objects, like a point object consisting of two integers, those being the x and y coordinates. Unions are typically used in situation where an object can be one of many things but only one at a time, such as a typeless storage system. See also, tagged union, union operator. External links: Boost variant, a type-safe alternative to C++ unions, MSDN, classes, structures and unions, for examples and syntax, differences between union and structure, difference between struct and union in C++.